Welcome to Deep Dive into Knowledge.
Welcome to Deep Dive into Knowledge. We have all stood at a window on a quiet afternoon, perhaps with a warm cup of tea in hand, just watching a rainstorm move across the landscape. You hear that gentle, rhythmic drumming against the glass. You watch the streaks of water merge and race downward. And in that moment, there is this instinctive, almost universal feeling that washes over you. You feel that the rain is something entirely fresh. It feels like a renewal, I suppose, a literal washing clean of the world, bringing new life to the soil and the streets. It is an experience so incredibly familiar, so profoundly ordinary, that we rarely stop to question it. We simply accept it. Yet there is a quiet, unsettling paradox hidden within those falling drops. That feeling of absolute newness is, in fact, a complete illusion. The ordinary droplets hitting the glass hide an inescapable, unimaginably deep pattern. The water you see falling from the sky is not new at all. It holds secrets and histories that go back further than human comprehension can easily grasp. It is a system of such staggering scale and complexity that it makes the everyday occurrence of a rainstorm seem almost bizarre once you truly look at the mechanics behind it. Today, this ordinary phenomenon deserves our quiet, undivided attention. We are going to explore the hidden, bizarre, and incredibly ancient life of a single raindrop in depth. We will trace its journey, understand the invisible architecture that builds it, and uncover the silent forces that guide it from the highest reaches of the atmosphere down to the earth beneath your feet. So to begin this journey, could you explain for us, just how old is the water falling on our roofs, actually?
Well, it is quite an astonishing reality to consider. The water falling is rain today. It has been circling this planet for billions of years. When we speak of the rain you are drinking or the rain washing your roof, we are quite literally talking about dinosaur water.
Dinosaur water.
Exactly.
Yeah.
The Earth has maintained essentially the exact same quantity of water on its surface for roughly 4 billion years. None of it simply disappears into the void, and, well, no truly new water is created. Every single drop is endlessly, tirelessly recycled.
So you're saying there is no new water being generated deep in the Earth's crust or arriving from space in any meaningful amount. We are just using the exact same water over and over again.
Yes, that is precisely it. The particular molecules of water raining down outside your window right now, they may well have been drunk by a dinosaur 65 million years ago. They might have been locked away, frozen solid in a polar ice cap for 100,000 years, or dissolved silently in an underground aquifer for millennia. Those same molecules could have evaporated from the surface of the Indian Ocean just last month, only to condense into a cloud above your city last night. It is one of the most elegant perpetual systems our planet has ever devised.
If we look at it that way, it is rather like observing Earth as a colossal sealed glass terrarium.
That is a very apt way to look at it.
The moisture is trapped inside, simply changing forms from ice to liquid to gas and moving around. But if we are dealing with such unimaginable volumes of water, how does it manage to constantly lift off the ground to keep this massive cycle in motion?
The sheer scale of the mechanics is staggering, really. And the engine driving this entire terrarium, as you call it, is the sun. Every single day, the sun's thermal energy heats the surface of our oceans, lakes, and rivers. This gives the liquid water molecules enough kinetic energy to break their physical bonds with one another and rise up into the air as an invisible vapor. To put a number to it, the sun turns roughly 1.2 trillion tons of ocean water into vapor every single day.
1 trillion tons. The scale of that is just hard to wrap my head around.
It is massive.
But it is not just the oceans doing all the lifting, is it? We have massive land masses that also contribute to this atmospheric moisture.
Yes, and plants are incredibly crucial to this cycle through a process known as transpiration. They pull liquid water up through their root systems and release it as vapor through microscopic pores in their leaves.
I see. So the forests are essentially breathing out water.
Precisely. In the Amazon rainforest, for instance, the sheer volume of transpiration from the vegetation creates phenomena known as flying rivers.
Flying rivers? You mean massive currents of water just flowing through the air, completely unseen?
Yes, invisible, immense atmospheric currents of water vapor flowing westward across South America. And they actually carry more water than the physical Amazon River itself.
Wait, really? There is more water flowing above the forest canopy in the air than in the actual river on the ground.
Yes, it is quite remarkable, and this reveals just how interconnected the system is. If you introduce local deforestation in the Amazon, you aren't just clearing land, you are physically severing these flying rivers.
Oh, wow.
That directly disrupts rainfall thousands of kilometers away in regions that entirely depend on that atmospheric moisture arriving.
Okay, so we have these massive, invisible rivers of vapor floating above us. But, well, there is a huge physical gap between an invisible gas and a heavy drop of liquid water. How does it cross that gap? I mean, it cannot just spontaneously decide to condense out of empty space, can it?
It hit on the exact mechanism that baffled observers for centuries. Water vapor cannot condense efficiently from perfectly clean air.
Right.
For a liquid droplet to form from a gas, the vapor molecules absolutely require a microscopic solid structure to cluster around. We call this a cloud condensation nucleus.
A nucleus, okay.
Without these tiny solid particles, the air can actually become supersaturated, meaning it holds far more vapor than it theoretically should without ever producing a single cloud or drop of rain.
So the water vapor is just up there suspended, waiting for something to grab onto. What exactly is it grabbing?
The atmosphere is full of this necessary microscopic debris. It is a mixture of desert dust lifted by the winds, smoke particles from fires, biological matter like fungal spores and bacteria, and crucially, sea salt.
Sea salt. How does salt get high enough into the atmosphere to form clouds?
When waves crash and ocean spray evaporates, it leaves behind microscopic crystals of salt suspended in the wind. And sea salt is remarkably effective as a condensation nucleus because it is hygroscopic.
Meaning it attracts water.
Exactly. It actively attracts and binds water molecules to itself.
So the ocean does not just provide the moisture for the rain, it is also providing the tiny seeds around which the raindrops themselves are born.
Yes, it is a very elegant process.
There is a beautiful symmetry to that. Now, if we think about the atmosphere where these seeds are gathering, it brings to mind thunderstorms. When you watch a severe storm, you see the violent energy of lightning tearing across the sky. Is that electricity just a byproduct, or does it actually play a role in this microscopic architecture of the rain?
It plays a profound role, actually. Large storm clouds develop immense electrical fields due to the friction and movement of ice and water within them. When a lightning bolt strikes, it tears through the atmosphere at temperatures reaching 30,000 Kelvin.
Goodness.
Yes, that is roughly 5 times hotter than the surface of the sun.
That kind of heat must cause a massive chemical reaction. I know that is what creates thunder, that explosive pressure wave from the heat. And just as a quick aside, the old trick for calculating how far away a storm is, does that actually work?
Yes, it does. Because light travels almost instantaneously, while sound takes about 3 seconds to travel 1 kilometer, you can easily calculate your distance from a strike simply by counting the seconds between the flash and the thunder and dividing by 3.
That is wonderfully simple.
It is. But returning to the rain, those 30,000 Kelvin lightning strikes, which occur about 1.4 billion times a year globally, do something else. They create intense bursts of atmospheric ionization and forged nitrogen oxides.
Let me make sure I understand this. The lightning is actually cooking the air and creating new particles from the gases.
Exactly. These newly forged nitrogen oxides and ions actually serve as additional condensation nuclei.
Oh, I see.
So the electrical discharge itself is actively helping to generate the very rain that falls from the storm.
So the storm is practically building itself. But let's follow that newly formed droplet as it starts to fall. For as long as humanity has been drawing, painting, or designing weather icons, we have universally illustrated raindrops as teardrops, a round base tapering to a sharp, pointed top. Why is our collective visual understanding of a raindrop completely wrong?
It is one of the most enduring myths in popular culture. Real rain simply does not look like a teardrop. The actual shape is dictated entirely by a physical battle between its size, its surface tension, and the physics of its descent. Very small drops, those less than a millimeter across, are perfectly spherical. The surface tension of the water is strong enough to pull them into a flawless ball.
But they do not stay that small.
No, they do not. As the drop gathers more water and grows larger, it falls faster. As it accelerates downward, the air resistance pushing up against the bottom of the drop begins to overcome the surface tension, pulling it into a sphere.
So it flattens out.
Yes. Medium-sized drops, around 2 to 3 millimeters, become flattened on the bottom. They end up looking like an oblate spheroid, much like the shape of a hamburger bun.
A hamburger bun falling from the sky. That is definitely not what we are taught to draw in school. What happens if it keeps growing?
If the drop continues to grow, approaching 4 or 5 millimeters, that air pressure pushes so hard into the flattened bottom that the drop develops a deep indent. It balloons out into a parachute shape.
A parachute.
Yes. And finally, if the drop exceeds about 4.5 millimeters, the parachute becomes completely unstable. It violently tears apart into a cluster of smaller spherical drops. You will never see a teardrop shape in nature.
Knowing that they tear apart so easily and knowing that they start out clustered around microscopic specks of dust or salt, there is a massive size gap there. A microscopic cloud droplet is 1,000,000 times lighter than a fully formed raindrop.
It is.
How does it manage to cross that gap and actually survive a journey of several kilometers down to the surface?
It is a perilous journey, and it happens via two completely distinct paths, depending entirely on the temperature of the cloud. In warm clouds, the process is known as collision coalescence.
Collision coalescence.
Think of it like this. A slightly larger droplet will fall just a bit faster than the microscopic ones around it. As it falls, it acts like a sweep, physically colliding with smaller droplets and absorbing them.
Right.
The larger it gets, the faster it falls, and the more drops it sweeps up. It is an accelerating snowball effect of liquid. It must absorb roughly 1,000,000 cloud droplets to become heavy enough to fall to Earth.
1,000,000 droplets just to make a single raindrop. The sheer volume of collisions happening above our heads is incredible. But you mentioned a second path for cold clouds.
Yes, and the true surprise lies in cold clouds, which operate through something called the Bergeron-Findeisen process.
That sounds rather complex.
It is, but in the freezing upper altitudes of a storm, clouds contain a mix of supercooled liquid water that is below freezing, but has not turned to solid ice and actual solid ice crystals.
Wait, why wouldn't all of it just freeze if the temperature is below zero?
Because liquid water needs an active freezing nucleus, much like it needs a condensation nucleus, to turn into ice efficiently. So you end up with this volatile mix of ice and supercooled liquid floating together.
I see.
And here's the crucial mechanism. The saturation vapor pressure over ice is lower than it is over liquid water.
Hold on, let me translate that. Saturation vapor pressure, put simply, are you saying the ice essentially has a stronger pulling power and it is stealing the water vapor right out of the surrounding air?
That is exactly it. The ice crystals rapidly draw vapor directly from the air. This causes the surrounding supercooled liquid droplets to evaporate just to replace the vapor that the ice just stole.
Oh.
The ice crystals grow large and heavy entirely at the expense of the liquid drops.
So the ice is cannibalizing the liquid water to grow heavy enough to fall?
Precisely. And this means that the vast majority of all rain, even the warm torrential downpours you might experience in a tropical storm, actually begins its life as snow and ice crystals high in the freezing upper atmosphere.
That is incredible.
It simply melts into liquid rain as it descends into the warmer air near the surface.
So the next time you get caught in a warm, muggy summer downpour, you are actually being hit by melted snow. That shifts the perspective entirely. But this journey downward is not always successful, is it? There are times when the sky seems heavy, the clouds are dark, and you can smell the rain coming, yet the ground remains completely dry. What is happening when this meticulous cycle just seems to fail midair?
You are describing a visually stunning phenomenon known as virga. Virga is essentially phantom rain.
Phantom rain?
Yes. It occurs when rain or ice crystals successfully form and fall from the cloud base. But the air beneath the cloud is exceptionally warm and dry. As the rain falls into this dry layer, the heat and lack of moisture cause it to completely evaporate before a single drop can hit the ground.
So it just vanishes into thin air.
Exactly. If you look at the sky, you can see these beautiful, sweeping gray curtains of precipitation hanging beneath the clouds. They often curve gracefully as they are caught in different wind speeds, but you can see a distinct line where they just end. They never touch the earth.
That must be so strange to witness.
It is a common sight in arid climates, and it can be a rather agonizing experience during a drought. The sky provides the visual promise of a downpour, while the earth below receives nothing at all.
If virga is this dry, empty teasing from the sky, let's look at what happens when the geography forces the exact opposite. Where on this planet does this atmospheric system get squeezed the hardest, pushing out the absolute most water?
That extreme opposite is found in orographic rainfall. This happens when geography literally forces the atmosphere's hand. When moist winds travel across flat terrain and suddenly encounter a towering mountain range, the air has nowhere to go but up.
Right.
As it is forced rapidly upward into the colder altitudes, it cools, the moisture condenses rapidly, and it drops tremendous amounts of rain on the windward side of the mountains.
It is literally like wringing out a wet cloth over the landscape.
Exactly. And the title for the highest average annual rainfall on Earth belongs to a village called Mawsynram, located in the state of Meghalaya in India.
Just to put that into perspective, how much rain are we actually talking about?
Ma Sinram receives a staggering 11,872 millimeters of rain a year. The warm monsoon winds from the Bay of Bengal slam directly into the Kazi Hills there, creating massive orographic lift.
Goodness.
The rain can fall continuously for weeks at a time.
Over 11 meters of rain. How does a community even function when the environment is trying to wash them away on a daily basis?
To survive, the indigenous Kazi people have engineered brilliant adaptations. They create soundproofed roofs to dull the deafening constant roar of the downpours. They weave full-body umbrellas known as nups that look almost like a woven turtle shell, allowing them to work in the fields.
Oh, I see.
But most remarkably, over centuries, they have learned to train the roots of living rubber trees to span across raging rivers.
Wait, living roots? Why not just build a timber bridge?
Because in an environment that wet, dead timber would rot away in a matter of months due to fungal growth. But a living root bridge actually grows stronger and more robust in the constant moisture. It heals itself and anchors deeper into the soil.
That is fascinating.
It is a perfect biological adaptation to an extreme weather system.
So the landscape forces the rain, and humans find a way to adapt to it. But we do not always just passively adapt, do we? We also try to actively control or alter this weather, sometimes by accident and sometimes on purpose. What happens when our modern actions intersect with this ancient cycle?
The impacts are profound. On the unintentional side, we have the creation of acid rain. When human industries burn fossil fuels, they release vast quantities of sulfur dioxide and nitrogen oxides into the air.
Right.
These interact directly with the water vapor we talked about earlier to form sulfuric and nitric acids. Natural rain is slightly acidic anyway, around a pH of 5.6, due to atmospheric carbon dioxide. But this human-caused acid rain can drop below a pH of 4.0.
And because the cycle touches everything, that acid falls back down onto the entire terrarium.
Yes. It slowly weathers stone buildings, acidifies lakes to the point where aquatic life struggles, and strips the protective nutrients away from forest. That is the accidental side. On the intentional side, humanity has actively attempted to force the sky to rain through a process called cloud seeding.
How do you force a cloud to rain? We just discussed how massive and energetic these systems are.
We do it by exploiting the Bergeron-Findeisen process we discussed earlier. Cloud seeding involves aircraft or ground generators dispersing particles, very often a chemical called silver iodide, directly into cloud systems.
Why silver iodide specifically? Does it just act like dust?
It is much more specific than dust. The crystalline structure of silver iodide is remarkably similar to the physical structure of natural ice. These particles act as highly effective artificial freezing nuclei.
Oh, I understand now.
They trick the supercooled liquid in the cloud into freezing around them, creating heavy ice crystals that will then fall and melt into rain. It is a massive undertaking in some regions. China, for instance, operates an enormous weather modification program employing over 37,000 people, aiming to systematically force rainfall over vast, drought-prone agricultural regions.
They're essentially hacking the cloud's internal physics. But if we pull back and look at the whole picture, that brings us to a broader, perhaps more urgent context. If this beautiful, complex cycle has run in a state of balance for 4 billion years, how is it reacting to the rapid global warming of our current era?
It is reacting exactly as the laws of physics dictate, specifically through a thermodynamic principle called the Clausius-Clapeyron equation.
Okay, before we get lost in the physics, what does that equation actually mean for us on the ground?
In simple terms, this equation tells us that the warmer the air gets, the more kinetic energy it has to hold onto water vapor before it is forced to condense.
Right.
For every single degree Celsius the atmosphere warms, its capacity to hold water vapor increases by about 7%.
So a warmer atmosphere is holding onto a massive amount of extra invisible water.
Exactly. And this creates a severe global imbalance. Because the air can hold so much more moisture, when the physical conditions finally force that moisture to condense and fall, we see much heavier, more intense, and highly destructive rainfall events. The atmosphere is dumping its larger payload all at once.
But if it is holding more water and raining harder in some places, why are we also seeing more extreme droughts?
Because it is a two-way street. That warmer air does not just hold more water, it also demands more water. It increases evaporation rates everywhere. So when it isn't raining, that superheated atmosphere is pulling moisture out of the soil far more rapidly than it used to. In regions where it isn't actively raining, droughts are intensifying at an alarming rate because the ground is being dried out faster.
So the extremes on both ends are being amplified. The wet gets dangerously wet, and the dry gets dangerously dry.
Yes. We are no longer guessing about this. We are watching this ancient cycle shift in real time from space. Instruments like the GRACE and GPM satellites monitor the Earth's shifting gravity and precipitation fields.
And what do they show us?
They allow us to actually see these massive rivers of moisture accelerating and changing their historical pathways. The terrarium is heating up, and the water cycle is visibly straining under the new pressure.
It is a sobering reality to consider just how deeply we are affecting something so fundamental.
I would offer this quiet thought. The next time you see rain falling, I invite you to consider the journey of the very next raindrop that strikes the window. If every single molecule of water has cycled through every ocean, through every ice age, and through countless forms of life for 4 billion years without a single drop being lost, does that make a simple glass of water the most ordinary thing in the world, or does it make it the most extraordinary thing you will encounter today?
Simply taking the time to look closely at a single drop of rain reveals the history of the entire planet. It connects the dinosaurs, the ice ages, and the vast oceans to a quiet afternoon by the window. It shifts our perspective from the mundane to the miraculous. Another thoughtful topic will be explored in the next episode. Until then, the next time the sky darkens and the rain begins to fall, we invite you to pause and reflect quietly on the invisible ancient history falling from the sky. Farewell, and thank you for listening.